Great, thanks, Tom. Hey, everyone, welcome back. Hope you had a good lecture this morning. So yeah, it's my last lecture today. So I guess yesterday we spoke about a number of things. We spoke about high dimensional networks, describing high dimensional states as well as lower dimensional states. So it's this PEPs and mirror, these PEPs and mirror ansatzes. I guess then we switched gears and started talking about holography, right? So like listed a number of possible confusions or things that had been puzzles in the past. And then I guess we discussed a very simple toy model, this 3-qubit code, which resolved some of those. So 3-qubit code was demonstrating that one can have like that things like the Ryo-Takayanagi formula with a correction term that sort of sees into the bulk, part of the bulk, that might kind of make sense. That this idea of being able to reconstruct and operate on several overlapping subsystems is not a contradiction, even if all these subsystems do not have any common support in the end. So that's nice. I guess something that was not really a part of the model was any kind of geometry, right? There was a single bulk site, and I guess there was only the option that this bulk site was included in the entanglement wedge or not. So now we want to go about fixing that. Okay, so there we go. So my Zoom looks kind of funny. Okay, and so the idea will be, of course, to use tensor networks, right? Because already when we discussed mirror, we saw that somehow to compute entropy or to bound the entropy of a boundary region or a subsystem, it was useful to look into the bulk. So somehow it was useful to sort of go up in the network to find the optimal way of cutting sort of one piece of the boundary from its complement. And so that will be the idea. And so actually in the first part of this lecture today, I want to focus simply on entropy and its scaling. So basically trying to reproduce the Ryo-Takayanagi formula, just the one, that say sees geometry without any bulk correction. And then we basically want to combine what we achieved then with this idea of codes, of error correcting codes, and define holographic codes, holographic mappings, again, using tensor networks. So maybe just, to get us started. So we defined this 3-qubit code yesterday. So it came with many code states, right? For every state of the bulk, there was a corresponding state of the boundary. So if you sort of went back to the formulas that we wrote down and you asked, okay, you computed this code state corresponding to encoding just a 0 state, it turns out that that state would just look as follows. Just an equal superposition from j equals 0 to 2 of a state as j, j, j. Okay, that's just because I is equal to 0, right? In general, the formula was a sum over j comma j plus I comma j minus I. So this state is, I guess, sometimes it's called the GHZ state. Doesn't really matter. We can think of it as a tensor, right? And it has the interesting property that the entropy of any single subsystem is log 3, as well as the entropy of any 2 subsystems, right? Because it's a pure state of 3 subsystems. The entropy of any single subsystem must be equal to the entropy of the complement. And it's easy to see, right, that the entropy of, say, A is log 3 because A is, as entangled as it can be with BC. So entangled on a 3-dimensional subspace. Okay, so we can sort of think of that, right? So somehow pictorially, sort of, if you think of this as a sort of a very coarse bulk, we can sort of identify this with, say, a situation where, whoop, looks a bit horrible. Where we have 3 systems, A, B, and C, and well, the RT surfaces are kind of those, right? And then sort of, we can sort of, say computing the entropy of subsystem A, well, in this picture would be, the area of the surface, whereas in this tensor, from the perspective of the tensor, it would just be the most economic way of cutting off or cutting, well, this network, this very trivial network into 2 pieces, such that one piece only contains A and the other piece only contains BC, right? So if I want to separate A from BC in this picture, there's two ways of doing it. I can either cut here or I can cut here. If I cut like so, I'm only cutting a single bond of dimension 3. If I'm cutting like so, I would be cutting 2 bonds of dimension 3, right? So in total dimension 9. So cutting like so gives me a better bound. That gives me this upper bound of log 3. And it turns out that in this state, that's actually saturated. Okay. So you could think of sort of this particular code state of the 3-qubit code as being an example. Maybe let me just fix the picture up a little bit. So this pink one, here I'm cutting a single bond of dimension 3. So this gives me sort of this log 3 bound on entropy. Whereas if I cut it here, this would give me a bound that's more like log 9, twice log 3. And indeed, That would be a bit like if if I looked at the non-minimal surface, that's like that's this one rather than this one over here. Okay, so that's sort of the cartoonish picture. And now the idea of the question is just, can we glue together many of these states, many of these tensors together to get a many-body state that maybe still satisfies something like the Ryo-Takanagi formula, right? So you could say this tensor satisfies some kind of discrete version of Ryo-Takanagi because we can compute entropy. We can not only bound it, but we can compute it by cutting, right? Cutting the tensor network in, by a minimal cut in a way that separates the system interested in from the component. So maybe I'll just write this down. So entropy of A, as well as all the other single subsystems, is just log3. We computed this yesterday. Okay, well, how are we going to do this? We're going to take this beautiful picture of a tensor network that in some sense, tries to approximate the geometry of the hyperbolic disk in some way, right? It's of course discrete, so it can capture all symmetries, but it's some part of, something that looks maybe like some fairly regular tiling, maybe not so regular in this case. So the idea will be, we want to somehow discretize, a geometry we're interested in, and we just place tensors, in the right way, and then we connect them up. And how do we want to connect them? Well, we kind of what like we saw in this picture here, that basically an edge in the tensor network basically corresponds to sort of a piece of area, right? Of area sort of that's orthogonal transversal, orthogonal to the edge. Okay. So that's kind of the mapping. So I guess I won't be super precise how, if you are given a geometry, how you should set up this network, but you can just think of it the other way around. You can start with some graph, and whatever kind of cuts in the graph are, that's supposed to be the discrete analogs of some continuous minimal surface in a continuous geometry. Okay. So what's interesting about this network is that it's unlike MPS and PEPS, but like Mera in the sense that it's a two-dimensional network, and a network laid out in 2 dimensions. But the only dangling legs, they are here at the boundary. They are in a one-dimensional, system, if you want. They form a one-dimensional system. So this picture describes a state of, if you wish, a quantum system on a discrete circle, right? And that's this one over here. Those are the only dangling legs. Everything else is being contracted in this network. Okay. But of course, there's nothing special about this particular picture. I could have taken any graph with a bunch of dangling legs and used this to define a quantum state. That's just the most general definition of a tensor network. But we'll always draw these pictures today because we're interested in modeling aspects of, say, AdS, CFT. So maybe just to write down a concrete formula, I guess we discussed that we can think of these states sort of in 2 ways. We can either take a bunch of tensors, one for each vertex, and then project or contract pairs of indices. Another way of thinking about them is to take lots of maximally entangled states, which are the links, and then projecting parts of them on tensors. So I'm going to take the second perspective today, just for convenience of calculating. So the idea will be, we are going to take, so I'll write down a formula. We'll talk about what it means. So I want to write down a formula, sort of a generic formula for an arbitrary state of this form described by such a tensor network, and the state of I guess I call it the boundary state, but I just mean the state defined by this picture, by this network. Okay. So here's a sort of a 2-step process by which I can write down a concrete formula for the state. So I'm going to take a tensor product, a big tensor product, over lots of maximally entangled states, one for each edge in the network, including these dangling legs, which I'm just going to think of, again, an edge. So lots of maximally entangled states. And so this is a big tensor product over all edges. I'll denote those by x and y, x tilde y. So x tilde y means there's an edge between vertex x and vertex y. So imagine that maybe this is x, this is y, and there's an edge here in between. Whoop, there's an edge here in between. Now, for each of these edges, I want to take a maximally entangled state. I'm just going to denote this maximally entangled state by xy, cat xy. Okay, so this guy is a maximally entangled state. So maximally entangled state, right, is something that looks like cat II, sum over I from 1 to some dimension d. And so it's a maximally entangled state of dimension d. And I'm not only including these edges by which that we use to contract, but also the dangling ones here. Okay. So what I wrote down here is a quantum state that has indices on the boundary as well as in the bulk, right? There's lots of indices at each vertex because I have not yet done any contraction. This is just a product of many maximally entangled states. You could think of it as sort of the skeleton of this graph that just consists of edges, but not vertices. And so it's kind of like, here's a bunch of edges. You could think of them as being arranged, but they have not yet been glued together by the tensors, by the vertex tensors. So there are subsystems, right? There's subsystems here corresponding to the boundary. Maybe I'll denote them in gray, and maybe, well, these are boundary things here. I guess in my picture, the dangling ones, they always, maybe they look like so. So these are subsystems of the state because they include the dangling legs. Maybe I'm going to write this down, including dangling edges or legs. And then there's more subsystems, right? There's this subsystem here, that subsystem, that subsystem. That's just like, all the sort of the subsystems where sort of half of these max entangled states end. And those are one-to-one corresponds with the tensors and with the vertices of this graph. Okay. So now what's missing is the part where I actually glue things together. And this I can achieve simply by applying a tensor product of bras. And namely, I just take a bra corresponding to the vertex tensor, or maybe I should take the complex conjugate, but we won't worry about this today. And multiply from the left. Okay, so I'm just taking another big tensor product, but now the next tensor product is over the vertices. Maybe I'll write X in bulk and only the ones on these sort of bulk sides, because that's where we place tensors. And maybe the tensor at side X is called Vx. So basically what I'm doing is this. Okay. So right, that means I would take a tensor here, V1, V2, V3, and so on. And maybe there was also Belp here, so it looks a bit nicer. Okay. So it's very important to note that these tensor products are not the same, right? This is a tensor product, or these cats, they're sort of not aligned, right? Because here I'm looking at the vertices, here I'm looking at the edges, but the Hilbert space associated to vertex it consists of many tensor factors, one for each edge, right? That's incident to this vertex. So it's, maybe as a simple example, say if I had, a max entangled state here, a max entangled state here, and one there, and now, well, I guess that's a very boring example, but okay. Now I want to glue this one together by, say, vertex tensor 1, vertex tensor 2. You see that some of the first max entangled state, right, it has two subsystems, 1 and 2. Those are the tensor factors on which this state lives. Maybe this one lives on subsystem 3 and 4. But this tensor here, right, that's a tensor on subsystems 2 and 3. So they're not aligned. So it's not like, so this is not the same as taking the inner product of this tensor with this max entangled state. It doesn't even make sense syntactically. Okay. So these guys, they are the tensors. That set up these vertices in the sort of bulk of this graph. Okay. So that's a completely general way of writing down an arbitrary tensor network state. And you could object that somehow there's a little bit of a strange notation convention thing going on here, because that's a state, right, on all these Hilbert spaces indicated here. And now I'm projecting only at these green sides, which probably I should have drawn in blue. So somehow, well, this thing looks like an inner product, right? But there's actually systems remaining. I could make this explicit by basically adding a big identity operator here. I could say, well, we take this whole thing, tensor identity on the boundary of all these boundary indices, right? That would make it maybe more clear. It's the same in this picture, right? I start with these bell pairs. Maybe these are the bulk vertices. These are the two dangling legs, as I'm sort of looking at it from the side. But I only do a projection here and there, whereas here I'm just doing an identity map, right? So writing down this identity map is a bit like adding identity maps here. Okay, and it's usually convention and confirmation that we omit identity maps when they're, well, just omit them by convention. Okay. Is there any question about this formula? So that's now a formula for a state, and it's exactly the state described by a general tensor network defined by a general graph. The only assumption being that the bond dimensions are all the same and equal to capital D. Okay, good. So maybe that's just for future reference. We'll sort of see, oops, or to sort of, write down one precise formula now. Okay, so I'll remove those. Now, now we have discussed a little bit about the state, and I'll ask one last time, how can we bound the entropy of a subsystem in such a state? I think we have discussed this in many cases for MPS, for PET, for MERA, and so on. So what's a general bound on entropy in an arbitrary tensor network? Entropy in any tensor networks, and particularly the one on the left, entropy always satisfies the same bound that we always discussed, right? Namely, entropy can be upper bounded by the max entropy, and max entropy of a subsystem, let's say the subsystem corresponding to these legs here, if you want. Well, how can I bound this, right? So what I always do is I have one subsystem A, then there's the complement. Let's say that's everything else here, right? That's all the other indices over here. A complement. And well, how do I get bounds on the entropy? I have to cut bonds of the tensor network until A and A complement are no longer connected. Okay. So there's lots of ways of doing it, right? I could, for example, cut like this. That's probably not a good idea. It's not very economic. It gives me a poor bound. The best way of cutting is, of course, by cutting, well, minimally. That gets me the tightest bound on entropy. So entropy in any tensor network satisfies the following bound, namely, we can always upper bound the max entropy by the logarithm of the dimensions corresponding to a minimal cut in the network. Okay, and here a minimal cut would probably look like this. Let's say like so. This would be one minimal cut. Sorry, that's a bit hard to read and ugly. And another minimal cut would be like this. There's two minimal cuts here, right? So if I look at this cut, okay, and I sort of drew it, how you would maybe draw it, geometrically, how you would dramatically draw the minimal surface. What I'm really doing is I'm cutting this bond, I'm cutting that bond, I'm cutting that one and that one, right? That's choosing any cut, and hence in particular the minimal cut gives me an upper bound entropy, namely logarithm of d, because that's a single bond dimension, to the size of the minimal cut, which is of course the same as the size of the minimal cut times log of one dimension. Okay, and you could call this a Ryo-Takayanagi bound, right? It's bounding entropy in terms of a minimal cut for the network. So maybe I'll call this the RT bound. Okay, and again, that's the number of bonds in a minimal cut. Maybe I'll write this down. So gamma A is min cut separating A from A complement. Yeah, and D is just a bond dimension of a single bond. Okay. Great. So that sounds promising, and it's of course exactly the same reasoning we used when we discussed Mera, right? When we got this logarithmic scaling, that was sort of our guess at what the best way of cutting Mera was. Okay. And the interesting question, of course, is when is this actually tight, this bound? Because if this bound was tight, then we would have sort of proved the Ryo-Takayanagi formula in our toy model. So to answer this question, maybe let's remind ourselves how this proof went. Okay, and hopefully that's not boring because we discussed it already once or twice, but I think it has some interesting geometry along with it. So maybe I want to duplicate this picture here so that we can draw. Okay. So how did this argument go? Let me just clean up the picture a little bit. Okay, well, we can do this maybe from scratch. Okay. So the idea was, right, we focus, we found these edges by which we could disconnect A from A complement. Let's say we pick those. Right now, A is disconnected from its complement. And now we just coarse grain the network, right? So that was the idea. So we are basically just thinking of everything in here as being one tensor. Maybe so this entire region of the network here, and we're just thinking of a single linear map from these pink to the boundary vertices. Maybe we call this one L as in left. And then the rest we also coarse grain. I mean, coarse graining is maybe a strange word. I just mean I block them together. I think of this sub-tensor network as a single gigantic tensor, just forgetting structure. Okay, so that's the other part of the tensor network. Okay. It's R. And so we see that actually the state psi, well, the state psi that's defined by the tensor network, we can think in the following way. We start with maximum entangled states, namely the ones corresponding to these bonds here. So we start with maximum entangled states, and we have sort of, say we have, how many do we have? Well, size of this minimal cut, many maximally entangled states of dimension D. And then, well, we apply a map L and another map R. Okay, and then out comes system A, out comes system B. That's sort of a cartoon, well, a coarse, sort of block together, coarse grained cartoon sort of picture of a way of producing the state, right? So these are these two blobs, and that's the maximum entanglement tiers, right? And that was basically the idea. So this picture shows that the rank of either reduced density matrix is at most the dimensionality here, the dimensionality here. Well, we have gamma A many max entanglements of dimension D. That's dimension D to the size of gamma A. Okay, that's a proof of the bound. Okay, so this implies the bound. But now it's interesting to ask, well, can we read off from this picture when this bound should be tight? Okay, and well, who has a guess? Like, what should L and R satisfy, such that entropy is not only bounded by the size of gamma times log D, but actually equal? If someone wants to make a guess. So what are the maps that don't? Yeah, Peter, I think you want.
Maybe that they're maximally entangled with respect to the smallest system.
That's right. If you think of this as a state, it would mean it's sort of as entangled as these pink guys. That's sort of from a state picture. And if you think of it as a linear operator, that would exactly be equivalent to saying this linear operator should be an isometry from the smaller to the larger system. Exactly. So if L and R are isometries, then this bound is actually saturated. So it would be saturated if L and R are isometries. So for example, unitary, but in general, of course, the minimal cut will be smaller than the size of the boundary in the interesting cases. So it can only be an isometry. Okay. So the question is, when are these coarse-grained pictures isometries? Well, one way of achieving this is, of course, to take lots of small isometries and hopefully compose them a good way to get a big isometry. And that's basically the idea behind what's known as the happy model. Short for, well, which is named after the initials of the authors. So the happy model, which is Harlow, Preskill, Kostovsky, and Yoshida, they basically said, well, let's just take small tensors that are isometric in any possible way. Such tensors are called perfect tensors. I'll define them formally in a moment. And then let's think about, in which cases L and R are actually isometries. So that was their idea. So they said, well, let's just choose tensors for constructing our network or our state that are called perfect, which means that they are isometries in any possible way. And I'll say what this means precisely in a moment. So if I take an arbitrary tensor, maybe this tensor here, right? There's lots of ways of thinking of this as a linear map. I can pick any subset of the legs as inputs, any subset of the legs as outputs. Now, such a map can, of course, only be isometric if the number of input legs is less or equal to the number of output legs, right? Otherwise, there's not enough space in the output. And I could demand that this tensor should be an isometry however I group the legs into input and output pairs, as long as the number of input legs is less or equal to the number of output legs. Okay, so here's two ways of doing it. There's of course many more. Maybe one way is I could say, well, I want those to be inputs and those to be outputs, right? Or I could choose those to be outputs and those to be inputs. Maybe that's a bit of a strange one, but okay. But whenever the number of inputs is less or equal to the number of outputs, I would like this tensor, it's always the same tensor, to define an isometry. Okay. There's lots of more options, of course. Of course, if I pick 3 of them to be inputs and 2 of them to be outputs, then there's no way of doing it. Okay. Okay, what's an example of such a tensor? Actually, we saw one when we discussed the 3-qubit code. Because if you think of this 3-qubit code, right? We had this 3-qubit code. And then we proved, okay, then we proved we can actually think of this tensor, we can write this in a different way. There's a unitary sitting here. And we can sort of think of can look at this object and this U is unitary, but it really means that basically if you take, if I rearrange the picture and I maybe move this one upwards, it's basically saying that this encoding map for the 3-qubit code, which in principle was a map from 1 to 3 indices, it says that even if I think of this one of the outputs as an input, it's still a unitary. Okay, it's maybe just an aside. Actually, the 3-qubit code is such an object. It's a perfect tensor with 4 legs, meaning that it's unitary from any 2 to any other 2. Okay. So that's just maybe a comment. So these things exist, and we actually saw them, and for good reasons, because they're supposed to form the elementary building blocks of our happy model. Okay. Now, okay, so that's a promising start, right? So basically we know that at the smallest scale, the single tensor behaves in a good way. It's isometric in any direction. Now the question is, if you look at an entire network like here, does that still define an isometry? Okay, so maybe I'll write down, I'll draw an example situation. So suppose we have maybe, I'm sorry, I have to copy this so that we actually have a nice example to discuss. Let's say we have a part of a tensor network that looks like this. Let's see, maybe like so, and maybe they all have 5 legs. Hopefully, sorry, all the pictures will again be in my write-up. Okay, so hopefully now all of them have, say, have the same number of legs. Okay, so imagine, so this is a one particular tensor network that we might be interested in, and maybe this part here, sorry, up to, whoa, what's going on? Is maybe subsystem A. Okay. In this particular network, I guess one way of choosing this minimal cut through the network, right, would be like this. This would be gamma A. Now, suppose this is all these tensors are perfect tensors. So what would be a sufficient condition for the Ricci-Nagy formula being satisfied with equality? Well, what we wanted to show is that this entire blue region, which is the 3 tensors here, they together form an isometry from those inputs here, the ones these edges that cross the RT surface, out to the boundary. And likewise, we want that this part of the network forms an isometry again going out to the boundary. Okay. So how could I convince you that that's in fact the case? Well, I could just orient the legs of all these tensors in such a way that the orientation they start being oriented away from the RT surface. So that's sort of the input of the isometry, right? That's sort of the part here. And here we're sort of going in, and well, at the boundary they should all point outwards. And now on the all remaining edges, I have to orient in a way that there's at least as many outputs as inputs. So there can be at most 2 inputs, such that each individual tensor can be thought of as an isometry. Okay. So I guess, for example, what I could do is I could, for example, probably do something like this. All right. So now this tensor has 2 inputs and 3 outputs, 1 input and 4 outputs, 2 inputs and 3 outputs. That would be one way of doing it, right? And now what we have achieved the following, namely we wrote this tensor L as a composition of many isometries, one after the other. It's nothing but a quantum circuit. Okay. And now we could do the same with a complement here. And if we managed to do so, we would have proved the RT formula. So if we can orient the edges such that at each vertex the number of inputs is less or equal to the number of outputs, and sort of maybe I'll write this as follows: and from the RT surface things always point away, either to A or they point away towards A, right? Or maybe I guess that's a weird way of writing it. But what I mean by this is that sort of at the RT surface they point away and they point into A at the boundary and into A complement at the other part of the boundary. Okay, so maybe that's not a great way. Maybe I should write it like this: they point away from A, and they sort of the edges at the boundary they point towards the boundary. Maybe I could just write it like this. Then this proves, that's sort of a graphical proof, that these maps L and R are isometries, just because they're now a composition of isometries, as in a quantum circuit, and the RT formula holds. So not just a bound, but it is now true, because of what we discussed here, L and R are isometries, that entropy of A is exactly equal to the size of minimal cut times log dimension. Okay. So now it's not clear, of course, if we can actually do this. But if we can, okay, now we just have a geometric problem. The geometric problem is, can we do this with orienting of edges or not? Okay. And it turns out that, okay, in general, of course, it's not always possible. There could be sort of bottlenecks in your graph, and then the strategy fails. But what the authors showed in their paper is that you can always do this if your graph is, is planar, if it satisfies some discrete version of negative curvature, and if the boundary system we're looking at is a single interval. So I think those were sufficient conditions. So in particular, sort of, in this example we showed here, they could show that that's always possible. Okay, so it only applies, and it doesn't apply in general, the strategy. So the model only works in somewhat special situations, you could say. But what's of course nice is that's really extremely concrete, right? You're just thinking about tensors and orienting the right way, and it's really just like a circuit picture. You can really understand how quantum information is flowing, right? You're drawing how it flows. So maybe to summarize, so I think it's very nice. It's very concrete and intuitive in a way what's going on, right? You're really sort of decomposing your state, basically. You're finding in a graphical way a Schmidt decomposition of your state. But maybe it's not the end of the story, because it only applies maybe doesn't apply in generality. Yeah. Of course, it applies in a case of much interest, which would be some kind of negatively curved regular tiling of hyperbolic disk, and sort of single interval subsystems. But one might still ask, is there another way of doing it? And maybe just because I said this a few times, kind of what we managed to do here by orienting these edges and having this unitarity or isometric nature, we really sort of, we can now sort of think of the bulk in some sense as a quantum circuit. Actually, it's many quantum circuits that are sort of routing the information through the network, right? So for any trusted boundary subsystem, you basically have two quantum circuits from the RT surface out to the two pieces of the boundary. Of course, if we look at a different boundary subsystem, you get different circuits. And because these tensors are perfect, they are gates, quantum gates in any possible way. That's where the flexibility comes from. So in some sense, it's usually unitarity is some kind of causality, right? But there's lots of kind of ways of thinking about the network here. There's not just like one flow of time, if you want, but many. Okay, so that's one model. Now I want to discuss another model, which is maybe less concrete in a way, but it's amenable to different techniques and that applies a bit more generally. And that's something we cooked up a little later, and it's based on random tensors. But maybe before that, I just want to ask if there's any questions about the happy model, how it works, why it works.
I have a question about that.
Yes.
So you had the interior edges, but I didn't understand why you put the arrows. Wasn't the point that the inputs were less than the outputs? But I can count that there are more outputs in the to A in that case.
Sorry, can you say again which direction?
Because you had those interior edges that you you applied arrows to. The ones that go from the middle dot, or sorry, the middle node to the outer nodes within.
Those here. You mean?
To the left of the boundary, gamma A.
Yes, like this one, say.
Because I don't understand why you have that interior line from the upper left to that one.
From here to here.
Yeah.
Right. Yeah. So the idea was I wanna basically find a way of building this quantum state by starting with maximum entanglement and then applying a unitary or an isometric map. Okay. And so here there's sort of 3 building blocks. So, but basically what I want to do is I want to start, maybe I can write this in a different way. I sort of start with sort of 3 max entangled states. They are the ones here. Let's say like this. Well, maybe I can try to draw it a bit better. This. Okay, and now I want to imagine I apply, time evolutions, little time evolutions, which means isometries, unitaries or more generally isometries. So somehow maybe I want to first apply, say, well, this time evolution here, right? And somehow I would, that would mean I apply sort of a little gate here. And now this one would have 4 outputs. Okay. And now in the next step, I would apply this one here. And I see now it has these strangely oriented arrows that you pointed out. Because this one points here, I can think of it as an input of the next step. Okay. So like this, right? And similarly, sorry, I think exactly, and similarly here. So this tensor I will now apply, this unitary will now apply here, and likewise here. And those guys I don't do anything to. So somehow what this this orientation gives me some kind of time order, right? It's kind of tells me and it gives me an order in which I can think of applying these gates step by step. Okay, and because I oriented them in a way that satisfied this constraint, I know that my tensors in that case I can always think of as an isometry. So it's always a good time evolution if you want. If I couldn't orient them in such a way, then somehow I would be applying a non-unitary, a non-isometric map at some point in time. And that would not preserve entanglement. That could create or destroy entanglement. But because there's a way of sorting things, kind of a sort of a time order, and this time order is encoded in some sense by the orientation of these edges, that sort of is consistent with treating every tensor as an isometry. That allows me then to conclude that these 3 tensors together, which is the same as this linear map L, is also an isometry. Does that sort of address your question, or is
I see better.
Okay.
I see better. Thank you.
Okay. So somehow there's no physical meaning, if you want, to the orientation. It's just a way of sort of convincing you by picture that there is a way of thinking about this part of the tensor network as a circuit, or as a composition of isometries. And that would have, of course, that would have not been valid if, if I would have oriented those, say, this way around. Somehow there would be a problem here because there's more inputs than outputs, right? And so this would not be a valid sort of proof or a valid way of convincing you that this thing defines an isometry. Okay. All right. Great. So now we'll discuss this other model, and hopefully we still have a little bit of time to then talk about codes. So the other model is called the random tensor network model. Okay. So that's something we proposed a little while ago. And the idea is very simple. The idea is just we want to take, instead of sort of fine-tuning these bulk tensors to be perfect, we're just going to take them at random, but we to pick the bond dimension to be really large. So we're going to choose random tensors at each vertex, independently of large bond dimension. So large D. Okay. So D is large. Yeah, and then we'll see what happens. Okay, in random, I should maybe say what random means. You could just take them to be random Gaussians. You could take them, you could pick them according from the Haar measure, which is the same as Gaussian except for the normalization, but normalization is anyways doesn't matter here because we will always normalize the quantum state back to norm 1, right? It's even we didn't even talk about that before. You could take them from to be random stabilizer states. We will see that the argument only requires sort of knowledge of low moments, basically the mean and the variance of the distribution. So there's lots of choices. But for concreteness, you could think Haar measure or random Gaussians. And what's the motivation? Well, one motivation, which is basically that one can show that random tensors are close to perfect with high probability. So in large bond dimensions, a tensor that you pick at random is approximately an isometry from any number of legs that's less than half. in a certain sense. So random tensors, perfect with high probability. Now, of course, if that was the only thing, then we were just back to the old model, but now, with the gigantic bond dimension, so maybe that would not be so interesting. The other sort of thing that conspires is kind of that there's also kind of a general position with each other. So somehow that helps, like it sort of destroys some sort of accidental symmetries that you might have and that decrease entropy. Maybe that's another intuition. Okay. And so one can show that in these random tensor network models, the RT formula holds approximately or in leading order. So random tensor networks, sorry, I guess I should have introduced this abbreviation. So RTN is for me random tensor networks. So random tensor network states satisfy RT formula approximately, namely, well, I guess we already know what this means. Entropy is, we say, approximately, so let's say in leading order, maybe that's constant corrections or very small corrections, proportional to the size. Same formula is here, right? Proportional to the size of the minimal cut. Okay. And that's going to be true with high probability for any graph and for any subsystem, not whether it's now planar or in higher dimension or whatnot. Doesn't matter, but of course, the size of the bond dimension might need to be much larger in one case than the other case. So the scaling of the bond dimension with the other parameters, the geometry, the volume, and so on, that's not obvious. But what I'm saying is if you fix a graph, if you fix your subsystem, then this will be true with high probability as the bond dimension increases, and it will maybe become clear from the argument why this is so. Okay, so that's kind of the appeal, and one can sort of prove this without sort of understanding much about geometry and about graphs, which is nice. Now, I want to maybe give you a sketch of how this works. Because it's, I think maybe there's some useful technical tools that you might learn this way. But just as a comment, so before we had this discussion, this very nice discussion, where one of you said, well, L should be max entangled on the smaller subsystem, right? Which basically says, its entropy, L, if you think of L as a quantum state, its entropy should be maximal. It should be the log dimension of this pink leg. And then I said, oh, exactly, that's exactly right. And it's actually equivalent to being isometry. Okay, so that means that the property that a tensor is perfect, which just means it's isometric with respect to any such splitting, is a property that only depends on entropies. Okay, so a tensor, in other words, a tensor is perfect if and only if it's the entropy of any subsystem is as large as it can be. Okay, and as large as it can be, of course, means logarithm of the dimension, but only if you look at less or equal to half of the system, okay? Because entropy of a system is equal to entropy of the complement. Okay. So in other words, and I guess we already observed this up here, right? Because this guy is also an isometry from 1 to 2 legs. A perfect tensor is nothing but a tensor that satisfies this discrete Ryo-Takayama formula. Which means that the claim I made here actually is a generalization of what's written here. Okay, so maybe that's maybe this was a bit quick. It's also not super important, but I just wanted to point out that the property of being special of being perfect is just a special case of satisfying the RT formula. Okay, because one can sort of, by treating an operator as a quantum state, one can capture the fact that this operator is an isometry by saying the entropy of the inputs should be maximal. All right, now maybe I want to talk a little bit why this is true. So why in a random tensor network state, the RT formula is approximately true. And the first observation that I want to make is, of course, that we already know that entropy cannot not be larger than what's written here, right? By the general RT bound that we did discuss at the beginning. So I only have to show that entropy is at least as large as what's written here. Yeah, maybe up to some small corrections. So we only need to prove a lower bound. And we mentioned at some point, entropy is an annoying quantity. There's these Renyi entropies, and the Renyi entropies for integer n, they're actually much nicer to work with. If this, well, for integer n larger equals to 2. And also the Renyi entropies with parameter larger than 1 are smaller than the von Neumann entropy. So since we're looking for a lower bound, it's of course enough then to prove a lower bound on the Renyi alpha entropy for alpha larger than 1. And we'll pick the first integer larger than 1, which is 2. Okay. The strategy will be to show enough to show that, well, a lower bound on the Renyi 2 entropy. Bound on Renyi 2 entropy of A. Just to remind you, that's minus logarithm of the trace of rho A squared. Okay. Now, we never worried about normalizing our tensor networks here. So maybe I also don't want to assume that rho is a normalized quantum state. So to make it a normalized quantum state, I should divide the stencil matrix by its trace. Okay. And because it appears with a square, I should divide by the trace of rho squared. So that's, of course, we didn't write this because we usually always deal with normalized quantum states. But you know, if I take these tensors at random and I contract them, then in general, the normal shrink. Okay, so I'll just want to be slightly precise about this. Okay, and the point why it was this good enough, because Renyi 2 entropy is always less equal to the phenomenon entropy, always less or equal to the max entropy, and the max entropy satisfies this upper bound. Okay, cool. Well, I guess we want to show a lower bound on entropy, and we're going to use the Renyi 2 entropy. Now I want to tell you the two key ingredients that matter here, and probably, I mean, I think you know them very well. In fact, maybe from Netta's lecture, well, one of them anyways. One of them is, of course, a replica trick, and that's the idea of, right, what's the key challenge here, right? The key challenge is computing this object, right, for my random tensor network. So that's a quadratic function of rho A, which means that if I can linearize it, but just taking 2 copies of rho A. Okay, and that's a special case of the replica trick. So that's one ingredient. Because there's only 2 copies, the only permutations that are around are swaps, and we call it the swap trick in quantum information, but it's the same as the replica trick. So that's the first ingredient. And the second ingredient then is we have to understand how tensors behave. If we look at two identical copies of a random tensor and we compute, for example, averages. So what I want to do is basically I want to compute the average of this green quantity with you. And hopefully we'll see that this average is something like d to the minus the size of the minimal cut. And then, you know, after taking minus the logarithm, we get exactly somehow the size of the minimal cut like here. Okay, so first ingredient is this swap trick. Is again special case of replica trick, and it's simply the following formula, namely trace of an arbitrary operator, say of this operator rho squared, is the same as taking 2 copies of the state rho A and then computing the expectation value of the swap operator. So swap operator I'll denote by f sub A. So f sub A is the operator. It's okay. So what's the Hilbert space here? Hilbert space here is 2 copies of the A Hilbert space, right? So there's 2 copies of the A Hilbert space, A and A. And the operator is the one that swaps the 2 copies. Right, and right, what's the proof? Well, if we just draw a picture, right? This is rho A, this is rho A. Now we are swapping, and then we're taking a trace. If you simplify the picture, you just see it's trace rho squared. Okay. Now we maybe don't want to deal with a reduced density matrix directly or with 2 copies of it. We just want to deal with 2 copies of the overall quantum state. So we can also write this, of course, by as follows. We can just take 2 copies of the entire tensor network state, and then acting with the same operator, you know, tensor an identity on the rest. And as said before, I will never write down identities today. So I'll just write FA here. And whenever I write FA, I mean the operator that swaps 2 copies of A, but it acts as trivially on the rest. Okay. So that's sort of this convention. F sub A always swaps the A's, and it never touches anything else. Okay. Very good. So now we have sort of linearized the problem in a way, well, at the expense of having to take 2 copies of our state. The other ingredient that we need is the following. We have to know, right? If you think about what's the state psi, right? So the state psi, we wrote a formula down here. And again, let me maybe remove these identities. for good measure? Well, cat psi contains all of these bras of the random tensors. So bra psi contains the corresponding cats. If you take 2 copies of psi, we have 2 copies of cat v bra v for any of these random tensors. So what we need to understand is somehow how random tensors behave if we take several copies of them. And the easiest question that you could ask is, oh, suppose you take a random tensor sitting, say, at one of these vertices, and you take 2 copies of it. So Vx is, in some Hilbert space, say dx, random, how random. Then the simplest question we could ask is, what's the expectation value of this object, right? So that's a random operator, and we could ask what is it equal to if we take its average. That's like it's the expectation value of this random variable. Okay. Now, what do we see? I mean, we see that this is a symmetric tensor. Okay, so it's a thing that doesn't change when we interchange the 2 copies of our Hilbert space. So it turns out because of the symmetric subspaces and reduced representation and so on, actually this thing is exactly proportional to the projection on the symmetric subspace. It's normalized as a quantum state because I will normalize this measure to be a probability measure. We pick things at random. So what this thing is going to be is basically going to be proportional. Maybe I'm just going to say this. It's going to be proportional to the projector on the symmetric subspace, which is identity plus swap. Okay, and I'm now using subscript x because we are swapping 2 copies of the x Hilbert space. Okay, so that's the idea. Okay, so we have the 2 key ingredients. We know how to linearize trace row squared, but at the expense of having to take 2 copies. 2 copies of psi contains 2 copies of all of these random tensors. If I average, them tensor by tensor, for each one I get a sum of identity plus swap. Okay. And now basically it's just a matter of doing a calculation. Right now we can sort of combine these things, and we can write down a formula for the, say, expected value of trace row a squared. Okay, and then one has to do a bit more math to show that it works with high probability and so on and so forth. But maybe we don't want to bother with this for now. Okay, so now I'm just thinking if I really want to run through this computation or not. But maybe I will. Yeah, let's see how it goes. Yeah, so maybe I'll just tell you sort of what will come out of it, or maybe we do a few steps. Okay, let's see. Are there any questions about what we wrote so far?
So how worried do we want to feel about the fact that there's an expectation value and log of the expectation is not the same as the expectation of the log?
We want to be very worried in principle. So we want to prove that, for example, the trace concentrates. And then somehow some of the bad part is this one, I think, actually, because for the other one can use Jensen's inequality to get a lower bound. And that one goes. So one of the 2 things is, I guess we're also dividing 2 expectation values, which is not the same as the expectation 1 of the ratio. So what you can do is you can basically show that actually everything here concentrates. For example, you could show the trace concentrates. You can kind of treat it as a scalar, and then you only have minus log of trace row a squared, and that you can lower bound using Jensen's inequality in terms of minus log of the expectation value. Yeah.
Thank you.
Good question. So I'll be super heuristic. I'll just compute the means and then claim things are concentrating or self-averaging or whatnot. Great. Any other question? We'll copy our formula from here. So that's the state we really care about now, right? Just for reference. Okay. So now maybe we actually, let's try to look at this in more detail, because I think there will be a nice answer. To simplify our bookkeeping a little bit, I mean, the things that we have to worry about are these random tensors, right? And we will take 2 copies of this entire tensor network states. We'll have 2 copies of this random tensor here. Whereas this thing, I mean, that's just some arbitrary quantum state. And of course, it will enter the calculation at some point, but let's not worry about it, just give it a name. So let's define as omega the state that's just, this tensor product of these maximally entangled states. And we'll worry about it at the end. And then we can just write omega here. So omega is kind of the state of the bulk in some sense before you actually do anything to it by making it by adding these random tensors. Okay. So now we want to look at trace row a squared, and as discussed before, we can write this as trace 2 copies of the tensor network state, and then swapping on the a's and not touching anything else. Okay, and I guess we want to compute an expectation value in the end. Okay, the thing we want to compute is the expectation value of this. All right. Okay. So now I'm just going to well, plug in the formulas. Okay, so I'm going to plug in these formulas. So I have you know, 2 copies of this state here. Maybe I'll just write this expectation value trace. Tensor product Vx. Now we have well, I guess sorry, 2 copies of each. 2 copies here, 2 copies there, 2 copies here, 2 copies of the last one. So these are the 2 copies of my quantum state, and I still have the swap operator flowing around here. Okay. Now remember that these tensors, they are sitting at bulk indices. Whereas this swap operator is swapping boundary Hilbert spaces, right? It's doing nothing to the bulk, right? Because I mean, we started with boundary state, and that's where this thing acts. So this guy, which is really missing an identity, is commuting with that operator, right? One acts on the bulk, and identity on the rest, and the other on the boundary. And likewise with this one here, right? So what I can do is I can, you know, depending on my taste, I can either move this guy to the very left, or I can move this one through, well, using cyclicity to the other side, and then through this swap operator. Okay, and then all the cats in the brass are sort of nicely aligned. So let's do that. And then we're almost done. This picture, hopefully for later. So we have 2 copies of omega. Now, tensor product, vertex tensors twice, and the swap operator. Okay, and now this expectation value is still hanging around here, but all of these tensors I'm going to choose independently. So what I can just do is I can just average these term by term, or factor by factor, right? Product, expectation value of product, the same as product expectation values if randomness is chosen independently. Okay. But now what happens if I average 2 copies of a tensor? Well, I get a sum identity plus swap. Okay, so that's now what's going to happen. So maybe just to be sure, here sort of we use the swap trick. Now in the next step, I'm going to know to use my knowledge of the statistics of random tensors. And again, that's sort of a very universal thing. It doesn't mean anything that's vaguely like the uniform distribution behaves like that. And what comes out is 2 copies here, and a big product of, well, identity plus swap. Then we multiply with the swap on A. Okay. So, phew, almost. So like it's beautiful to end a lecture series on a technical calculation. That's what everyone enjoys. Okay. So now actually we are almost done, because we see, well, we have a big product, and for each term we either choose identity or we choose to swap. Okay. In other words, we can replace this now by a sum over all possible subsets of my bulk, and the subset dictator tells me where I swap, and the complement is where I don't swap, right? So I'm just multiplying out all these products. So I can also write this as a big sum over all subsets M of the bulk, and then I've, you know, trace omega twice, and well, I'm swapping all these sites in M, and then I'm also swapping A. So maybe I'll just write this as a swap operator on the 2 copies of both A and M. Okay, so now who has a hunch of what, I mean, what is this thing equal to? The summoned. So now we just use the replica trick in reverse, right? Because what we see here is we have 2 copies of a quantum state, and we have a swap operator on some part of it. So that's exactly the same as trace. That's exactly the same as trace omega AM squared, which is 2 to the minus the Renyi 2 entropy. Okay, so sum over all subsets M by bulk, 2 to the minus Renyi 2 entropy of subsystem AM in this bulk state, in this state omega, the state that just consists of bell pairs of maximally entangled states, 1 for each edge of the graph. Okay. So now if you have a sum like this, of course it will be dominated, right, by this term that's sort of smallest, because everything here will be sort of quantized multiples log of the bond dimension. Okay. So the question is, for which subset of the bulk is this term minimized? And actually, what maybe you could ask before that, you could ask, what's the interpretation? What is actually this entropy equal to? Okay. So what is the state that we have? Okay, what's the state? The state is the state omega that just consists of bell pairs. It just consists of maximum entangled states, right? Let's say maybe like this. So it's kind of, yeah, again, it's the sort of skeleton of the graph. It's just a tensor product of many bell pairs, one for each edge. Now there's this boundary, okay? And so again, what are the Hilbert spaces? They're sort of sitting here, right? These are all these Hilbert spaces, but they're not tensors, right? They're just Hilbert spaces, okay? So now what am I doing? Something appeared on my screen, interesting. So now what are we doing? Well, we are computing entropy of a subsystem of this state. The subsystem always contains A. It never contains the rest of the boundary, but it contains some arbitrary part of these bulk size, right? So maybe this part here, maybe this is M. Maybe this is M. So what's the entropy of AM in this picture? What is generically, or in general, what's the entropy here? So I have a state that's just, bell pairs according to a graph. And I look at a subset of the vertices and I compute and I ask you, what is entropy in this state equal to? Well, clearly, if my subsystem is everything here, well, what's entropy of maximum entangled state? It's a pure state. So if I'm looking at both systems at the same time, entropy 0. If I have not access to no of the system, entropy 0. But if I look at half of a maximum entangled state, this is the only time when entropy is when I get a contribution to entropy. Okay, so it's exactly about the edges that leave this region M. Those are the ones that contribute entropy. Okay, so this term is equal to, well, log D, because that's somehow how things are quantized here, times the number of edges, well, let's say just the boundary of this region AM, if you want, right? So there's this region AM, it's this one, and then this is the boundary of it, okay? So what's really going on here? We're looking at parts of our bulk. We look at the boundary of a part of the bulk. That's a codimension 1 surface, okay? So that's exactly actually implementing this homology constraint that probably Netta talked about, right? Because homology is always a boundary of something else. So what we find here, okay, maybe just to write down now the conclusion. So what we found here is we have a basic sum of all possible such choice of M, and then right, entropy is D to the minus sort of the boundary of this region AM, and that's of course a cut homologous to A. Okay. And so it's clear, right? Everything except for the min cut gets suppressed by a factor 1 over D. So the leading contribution here is equal to D to the size of the minimal cut. And then, maybe there's multiple minimal cuts, so there's a little degeneracy, but everything else sort of gets suppressed as 1 over the bond dimension D, okay? Where this is the RT surface. Okay, so that's maybe that's a bit of technical, but that's sort of a calculation one we could do. Are there any questions? Well, either about the individual steps or what the point was. So maybe I didn't even say why we're done. Well, we computed that the trace of rho A squared is basically D to the minus size of the minimal cut. And then, well, I guess I neglected some proportionality constants here, right? So that's sort of, but that's being compensated because we're dividing by the trace here. So really so you can trust me when I say that if trace rho A squared is proportional to this number, then by taking minus logarithm of that, we get exactly size of the minimal cut times log of the bond dimension. Okay, so that's sort of one way. So basically what happened is it's kind of very interesting actually, right? This random tensor average led to a sort of a superposition over all cuts in the network, all surfaces, all potential RT surfaces, not just the minimal one. And each RT, well, each surface homologous to the boundary gave us a contribution to trace rho A squared, but all of them were suppressed by a factor 1 over the bond dimension except for the RT, well, for the minimal surfaces. So that's kind of a fun mechanism somehow. Okay. All right. Any questions? I'm just checking chat because some of these buttons are for some reason. Oh, here we go. So maybe we'll discuss a little bit what was achieved and how it sort of fits into the bigger picture. Let's discuss. So maybe first a first comment. So what did we manage to show? We managed to show that the Renyi 2 entropy, on average, for large bond dimensions, actually satisfies the RT formula. Okay. So it followed again by the sandwiching argument that also phenomenon entropy and the max entropy, well, they all satisfy this bound approximately. And that actually implies that the entanglement spectrum of the state is flat. So all entropies are basically, equal to log dimension times the size of the, are given by the RT formula. And that's something that's not true in holography, okay? Because there's interesting entanglement spectrum. Now it was understood recently that actually there is an analog of what's going on here in these random tensor networks in holography, and that's something called fixed area states. So fixed area states are states where you insert some constrained integrative path integral to fix the area of the RT surface for your boundary region. And then somehow that leads basically, it trivializes the entanglement spectrum, and then the behavior is very similar. And I guess something that I think the community is also trying to understand is how to push this analogy further. I find this a very interesting problem. And what are sort of the observables for which fixed areas or generalization of fixed area states sort of behave like random tensor networks. And indeed, right, and again, that was because of what Netta mentioned, right? Sort of even if you have the singular boundary when you do the replica trick, but the bulk is smoothed out by Einstein's equations, and that's kind of like, that's why the different Renyi, sort of the bulk geometries for different Renyi parameters, they're not like trivially related to each other. There's some like a non-trivial effect that leads to this non-trivial entanglement spectrum. So that's one comment. Maybe another comment that we could make is, maybe let's just stare again at this funny formula here, and let's give it a bit of a different interpretation. This expectation value of trace rho a squared that we found, I'm going to claim I can also understand this in a different way. I can think of this as the partition up to this sort of proportionality constant that I neglected. I can actually think of this, I claim, as a partition function of a classical statistical mechanics model. Okay. And well, how's this model defined? Well, remember we had this like big sum, right? Here, or this, for each vertex we had to decide, do I pick the identity or the swap term? That's kind of like in an Ising model, right? Where you pick spin up or spin down at each side. How about the boundary? On the boundary, we always swap the A part and we never swap the complement of A. That's like fixing boundary conditions of our Ising model. And I claim that actually if you looked at an Ising model at say inverse temperature log bond dimension, with the standard Ising interaction, that's exactly the same formula as we wrote here. Okay, so maybe I'll just write this down. So there's sort of, there's some, for each vertex, so including the boundary sites, maybe for each vertex, you pick a spin up or down. On A, you always pick, say, spin up. On a complement, you always pick spin down. And then you say something like, well, e to the minus log d times sort of an energy, sort of an Ising energy corresponding to the spin configuration. Right, and that means like if you have a bond, if the two spins are aligned, you get energy contribution 0, or if you pay energy cost 0, and if they're anti-aligned, you pay energy cost 1. Okay, that's exactly the same here, right? Because what you're really doing is you have the spin configuration. There's these domains where the spins are equal, and whenever you have a domain wall, you pay. And the domain walls in the statistical mechanic model, they correspond exactly to the RT surface or to these like cuts that we discussed before. So somehow you, right, sort of, again, we have a sort of this Ising model, boundary condition here say spin up, boundary condition there spin down. And then we are trying to, we're asking what's the minimal energy, what's the ground state energy of such a configuration? But clearly we want to fill this domain with spin up, this domain with spin down. And then the energy cost of ground state is proportional to this, to the size of this RT surface here. Okay. And if you study this model, right, at very low temperatures, then we would expect that this partition function is dominated by that. And low temperature, of course, means high inverse temperature, but it means high bond dimension. Okay, so this is basically inverse temperature. So large bond dimension limit is low temperature limit of this Ising model. And then, right, the log of this partition function, which is kind of the free energy, is being dominated by basically only contributions to ground state energy. And that's another way of thinking about this. And it's very a good way of thinking about it, because it basically leads very directly to generalization, to say higher, Renyi entropies and sort of other kind of expectation values. If instead of looking at some quadratic expression here, if you looked at, say, an nth Renyi entropy, well, what would happen? It turns out that that the replica trick, in that case, instead of swapping, you have a cyclic permutation. You're like gluing together the replicas in some staircase fashion. So you would again get a statistical mechanics model, but now the degrees of freedom are permutations. On one side, you have, say, a cyclic permutation. On the other side, you have an identity permutation. And the cost associated with an edge is somehow the difference between the two permutations measured in some natural metric, just some number of swaps needed to go from each other. So maybe I just want to say, this is sort of extremely natural generalization. To say, say higher replica tricks. I mean, in the sense of, more than two replicas. Let's say more than two replicas. More than two replicas. Okay, I think I should wrap up slowly, maybe in the next 5 minutes. Okay. So let's do that. And so maybe just to say, I mean, why would you ever want to look at more than two replicas if the entanglement spectrum is flat? There's other interesting questions you can ask your quantum state, right? For example, you can look at, you could ask, okay, right now we only looked at entropy, right? Entropy is kind of measuring the entanglement between A and A complement. You could also be interested in, say, the entanglement between two subsystems, A and B, but they don't cover the whole boundary. So the reduced state of AB is not pure. So let's say, right, there's sort of A, B, and then the rest. And you're interested in quantifying the entanglement between A and B. Now, if Patrick would have had time to talk about mixed state entanglement, he might have introduced to you various measures, various ways of measuring this entanglement. So for example, there's something called the reflected entropy, but that's one way of doing it. There's something else called the entanglement negativity. And then there's a bunch of other measures that are really hard to compute. Okay, but say for this entanglement negativity, one can use similar replica tricks, but now sort of these it's sort of a more interesting quantity than this one. So it corresponds to some interesting expectation value where you're doing one permutation on one part of the boundary, some other permutation on another part of the boundary, and so on. And then somehow it's really useful to have the statistical mechanical intuition, right? Where you can just think of this as a classical StatMech model. There's a, say, permutation boundary conditions here, other there, and you can sort of try to guess your way towards understanding by understanding sort of the low energy physics of this completely classical model. You will sort of understand, basically the behavior of these quantities in the quantum mechanical tensor network model, in this random tensor network model. So I would say sort of the appeal of the random tensor network model is that you can really you can compute lots of things by reducing them to classical, I mean, non-trivial, but classical questions about, permutations, permutation models, sort of generalized Ising models. Okay. So that's one thing where one could talk about a lot more. Another thing that I guess is this picture that I keep moving downwards is how about, I mean, going beyond states, right? We spent, I guess, the entire lecture talking about states. Ideally, I would have liked to talk for 10 or 15 minutes, actually, about codes, about, ways of actually mapping bulk to boundary. So we saw this yesterday in the 3Qubit code where we mapped one bulk degree of freedom to a three-side boundary. Now we have tensor networks. Of course, we can just combine both, right? And combining both would be like in this picture if you ignore these shaded regions. Right, so what we're doing here is we have the same tensor network structure as before, but now at each bulk side, we're adding an input. Okay, so now this picture corresponds, right? That's maybe, I guess it's, I hope it's clear, but maybe it's still weird. So maybe let me just take a copy of this one. The expense of running over time a minute or two. So this is this thing defined as state, right? We discussed this before. So now the only thing I'm doing is I'm adding new legs here at each bulk side. Every bulk side, I'm going to add one leg. And now I have a tensor that has bulk and boundary degrees of freedom. And such a tensor I can think of as a linear map, as a mapping from bulk to boundary degrees of freedom in the same way as in the 3Qubit toy model. And I could ask, what kind of properties does it satisfy? Does it satisfy properties that we hope or expect from holography, or does it not satisfy those? And again, one can do this in this happy model under some assumptions, or one can do it with random tensors. Okay. And so, for example, you could ask about, this subregion duality question, right? And what does this mean? This meant that it should be possible. Now we come to the second picture. It should be possible, right? The claim of subregion duality is that if you look at a degree of freedom inside this entanglement wedge here, it should be possible to reconstruct it from this boundary here. Right? And you could try to prove this again by sort of orienting arrows. If you oriented the arrows, somehow that would, what would that correspond to? That would be a bit like you have the left part of the network, you have the right part of the network, you have this entanglement according to the RT cut, but now you have two inputs, right? You have the input corresponding to entanglement wedge and to the complement, on the output on the A boundary and on the complement. So now again, if L and R were unitaries then or isometries, then you could decode the entanglement wedge from this output. So that's one way of doing it. The other is by computing entropy and using this decoupling story that Patrick mentioned, I think maybe in his last lecture. So that's one thing one could talk about. And I think that's, of course, that would have been nice to end on that and with a bit more time. Somehow, maybe just to give you a glimpse, I guess I wasted a lot of time talking about this particular calculation. The beautiful thing about this calculation that we spent time on is that it did not depend at all on the geometry of the object we looked at. So now you can do, for example, the following things. You can treat this object, this linear map, you can think of as a quantum state, and you can compute actually entropies of things like an entropy of some bulk legs. Right? So for example, to show that this entire thing defines a map, an isometry from bulk to boundary, the only thing I would have to do is I would have to compute the entropy of the bulk legs. And this I can do using Ryo-Taganagi. And Ryo-Taganagi would tell me, well, I just have to find a minimal cutting, separating the bulk from the boundary. And then there's, there's like sort of the area, I can cut sort of here at the side, or I can sort of chop off each bulk leg individually, and so on and so forth. And, one can think about this, but the key point is like all these like information theoretic questions we can now basically answer by just drawing pictures and by, cutting through our geometry and so on. So one can precisely understand when does subregion duality hold. One can also, talk about corrections to the entropy, about generalized entropy formula, islands, sort of toy versions of these islands that you heard about, and so on and so forth. So that's one thing. Maybe I'll just say some other keywords, and then I'll sort of wrap up if Tom allows.
Sure, sounds good. Yeah.
I just want to mention maybe a few things that we didn't have time to discuss, and I wasn't planning on discussing, but it would have been nice to talk about, right? So one is sort of this whole like error correction story in much more detail. So in which sense are Ryo-Taganagi actually related to, say, subregion duality and so on? There's a very nice story there. Something else is this thing we discussed last, I guess yesterday in the Q&A, sort of superpositions of geometries. Does that can one model and incorporate those into the network? How about Hamiltonians? Right? Is there like a consistent way of having a bulk, sort of effective Hamiltonian in the bulk, let's say local, and also a dual Hamiltonian on the boundary that's also local? That's not at all obvious, but that's something people have studied recently. Then one can we can talk about things like generous entropy formulas and its subtleties and so on, entanglement measures and so on. So these are just like a bunch of things. So I think there's lots that we don't understand about these models. But I hope it was still sort of fun. So I guess that was, it was my last lecture. So hopefully it came together a little bit, right? So this idea of tensor networks, right? Building quantum states based on geometry together with this, error correction idea, as a sort of means of building nice little toy models. I heard that Brian mentioned random circuits the other day and that, you all should do the calculation yourself. Maybe I guess I did maybe a toy version of that for you, so maybe that helps to get started. All right, so yeah, so I'll shut up now. So thanks a lot. And are there any questions?
Thanks, Michael. Okay, maybe we can take a few quick questions. We have a Q&A scheduled for Monday, and hopefully Michael will join us for that at 9 a.m. So you can ask more questions then. But let's take a few quick questions now, and then we can break. So this last fact that you mentioned about proving that it's an isometry,
Mhm.
You sort of, you do that, it's an average statement, right? As in it's it's an isometry on average, is that right?
Yeah, so I think good question. I mean, so all these things that we proved in average, they do hold with high probability, but the entropies are approximately, equal to the RT formula. And I guess there's some subtlety, and if I have a quantum state that's almost maximally entangled, how close is it to a unitary, say operator norm or something. So somehow there's some technicalities around this, but everything that we proved here on average, you will also be able to show with high probability. So that's not necessarily an issue.
I see.
Yeah.
Okay.
Good question.
Can I ask a pretty general question?
Sure.
What was you were talking about? But is there a picture where this tensor network reconstruction of the bulk, encoding of the bulk, is related to holographic complexity? I was thinking to something like, if you evolve in time, maybe the boundary state that would include like higher number of vertices in the bulk, and I wanted to know if the state becomes more complex. And so if I wanted to know if maybe that can be related in some way to holographic complexity, or if anyone tried to do that already.
Yeah. So one, I think one sort of interesting factor. So I guess I had the story before, like when in the situation where we have say this RT surface here, right? Then you can sort of orient these tensors such that they're unitary and so on. And that sort of says that, I mean, yeah, so that's okay. So that's one situation. You could also have a situation that you're say two RT surfaces, and then so the stuff in between can be unitary kind of, because it goes up and goes down again in size. And non-unitary evolutions are harder than unitary ones. So I think there's some story there. This is like Python's lunch story that some people have worked on. I think that's basically a relation that one could explore. So I think there is sort of I guess there's maybe heuristically one can sort of maybe understand sort of these kind of bottlenecks in tensor networks with some increase in complexity. I'm not sure I can say a super sharp statement there. I think in general, like what's really missing in all of these toy models is some like, I mean, especially if you want to see not just, if you don't want to just quantify complexity of a single state, but say see something evolving, I think none of these toy models really have any dynamics attached to them. So that's a bit unsatisfying, right? I mean, one could sort of hope maybe a picture where kind of you go from one time slice to another by sort of evolving your network, maybe by, I guess naively, maybe you would apply some kind of time evolution network and then you compress again in some geometric way. But I think that there's no model that really captures this as far as I'm aware. So maybe sort of slice by slice, you could draw an analogy, but relating the slices, I don't think there's any like nice model that people know. So that would be really, really nice to have actually.
Actually, I guess related to this question of dynamics. So I guess I'm still kind of confused about why people believe that you should be able to have local time evolution, because it seems like the way you get locality is like you fix this background and then you put your bulk degrees of freedom on top of it. But if you want like true time evolution, you have to like evolve this background too, right? And then you get non-locality. So like, yeah, I guess why do we expect that we should be able to model local evolution?
Yeah, I mean, I would say because say on the CFT side, your time evolution is somehow quasi-local or something, right? And then maybe effectively you can describe what's going on in your bulk to some extent, right? Maybe for some time, certainly in some local way. So somehow, so the idea of the question there would be to find, so what do you want actually? You would like say say local Hamiltonian in the bulk, and then maybe you would like to construct another local Hamiltonian in the boundary, which on the code subspace acts the same way or approximately the same way. So I think that would sort of reflect maybe what the expectations, and that's something that people I think achieved recently in some situations. Yeah, actually also say, well, both with the sort of an upgrade to the happy model, I think in higher dimensions, and also to random tensors. So yeah, so that's sort of very non-obvious, right? Because some of I guess we didn't discuss, but we saw this in the Putrid model, right? When you you can sort of take a local operator at a bulk site, and then you could push it out to the boundary. But of course, the further in you start, the less local it is on the boundary. So if you just say naively took a local Hamiltonian sort of on your, on this effective, bulk field theory that's kind of corresponding to these red legs. So I mean, I'm just saying words, right? What I mean is I just take a local Hamiltonian on this bulk Hilbert space corresponding to these red legs. Imagine these red legs, they're like qubits. They're like really, it's some effective description. It's like so few degrees of freedom, so low energy, it doesn't, doesn't impact your bulk. Like it's not like you're creating any significant backreaction or something. Then somehow, if you pushed out, say a two local term here to the boundary, right, it would sort of grow in size, and it's not clear that you can sort of truncate or sort of, maybe you can look at the density of the, how maybe the non-local terms are there. There's fewer of them than there's local ones, right? Because so this kind of analysis people have done in a certain scenario, and there's like some tricks, some Hamiltonian complexity that they use to actually show that you can find an equivalent quasi-local, I think, boundary Hamiltonian for any local bulk Hamiltonian in those models. Mostly just based on, I mean, the only input is really the subregion duality, actually. It's not like you don't need any other fine tuning, no, I think. Right.
Could I ask something?
Mm-hmm.
I'm a bit confused in the random tensor network model. If we average over all the tensors, then how do we create different states in the boundary? Or is that possible in this model? It seems like you only get one state if you're
very good. Yeah.
everything.
Yeah, so it's a bit unfortunate that I spent too much of today just talking about states, like here. Right? I mean, the same would be true in this happy model, right? If I don't have any, if I start with a network like this, I just get a single state, right? Once for each choice of tensors.
Yeah.
Or if you choose them at random, you get an ensemble of states, but somehow everything we discussed was true basically for a single realization.
Mm-hmm.
Some of the thing I very quickly said at the end, or towards the end, right, was that we can sort of upgrade these models, both the happy model, and I mean that was really what they achieved, as well as the random tensor network model, by adding to each tensor an auxiliary leg that's now dangling in the bulk. And so now it's still in random tensors, you would pick all of these as random tensors, but now they have, each of them has this additional leg. And then their claim would be, if you picked, say, all these tensors at random, and now you've picked them, then this thing defines a linear map that satisfies these properties that we would expect or hope from holography with high probability. So, picking all these tensors gives you not just a boundary state, it gives you a linear map from bulk to boundary. So like a whole dictionary. Does that make sense?
Yeah, that makes sense.
Okay.
And is it possible to count how many boundary states you would have? And then in some sense, say that only a small fraction of them have a geometrical bulk or something like that?
Yeah, no, that's a great question, actually. And somehow, right, so it's really the question, how large can you pick these dimensions, these bulk dimensions, such that this tensor still defines an isometry, so an encoding from bulk to boundary. And one sort of necessary constraint is, of course, that the bulk Hilbert space dimension is less equal to boundary Hilbert space dimension. And say negative curvature, that's sort of okay. Like if this was flat space, would be weird, right? Because the bulk is sort of this volume law on the bound. So it would still work, but you would have to pick those dimensions much smaller. So imagine these are, say, qubits or something low dimensional, and then all the in-plane bonds, they are really high dimensional. Then it would still be that sort of, even in, say, flat space, sort of this volume law associated to the qubits would be beaten by the area law of the other guy. Sorry, would beat the area law. Yeah. So sort of if you, so kind of the way you show this in happy is, again, by trying to orient these tensors in such a way that you actually see that you have an isometry now from bulk legs plus RT surface to the boundary. And that's possible sometimes under some assumptions. How you would do it in random tensor networks is you would sort of treat this entire thing as a state, and the state is now a state that has bulk as well as boundary indices. And now you would compute the entropy of the bulk part. And because Ryo-Takanagi holds in random tensor networks, you can just do this geometrically. So you could ask, what is the minimal way of cutting the tensor network in such a way that it separates all these bulk legs from all the boundary legs? And again, there's basically these two choices, right? These two extreme choices. Either you just chop off all these legs, that would correspond to log, say of this red dimension times the size of the bulk. And the other choice would be you cut sort of here, right? You cut sort of all the boundary legs. That would be log of this other bigger dimension times the size of the boundary. Okay, and so if this guy wins, you have an isometry. If that guy wins, actually you have an isometry the wrong way around. So you can choose both, right? You can also choose this one and then say, oh, let's again look at the small subspace of the bulk. That's a bit this bidirectional codes Annie mentioned yesterday. But sort of in the simplest case, you would kind of like this one to be the minimal one of the two. And then you would have proof that you have an isometry, you really have a good encoding of bulk to boundary. And you didn't have to do any random tensor calculation. You can just like leverage Ryuta-Genagi of this joint bulk boundary state. And you can similarly think about subregion duality and also just by computing entropy.
Thank you.
Okay. Yeah, let's finish there. And